Hi, everybody. Welcome to Lecture 12 in our series on the Trivium. That is the first three of the classical liberal arts grammar, rhetoric, and logic. We are today in the thick of our discussion of logic. We've talked about the logic of terms, and now today we're going to start wrapping up our discussion of the logic of propositions. I say start wrapping up because this lecture and the following two short lectures are all, it's kind of like a sub-series within the series. We're going to look at three kinds of what are called immediate inferences. Immediate inferences. So basically, how to derive knowledge from what we already know without having to build an argument or gather further evidence, that kind of thing. So let's jump into it. We see here Aristotle's famous square of opposition, and this will be your friend in working with opposites, as we're doing in this lecture. By the end of the lecture, we'll see this half a dozen times, you'll be able to understand this table a bit more clearly and know how to use it. That's our goal. Preliminaries. What are we even talking about, right? So this lecture and the following two, 13 and 14, are all related to operations with categorical propositions. That's what we've been looking at. Things like all S are P, something like that. The three operations are opposition, conversion, and obversion. Why are we looking at these things? Well, Hauser gives us the following explanation. Opposition, Hauser writes, helps us understand a proposition by seeing other concepts or other propositions that are opposed to it. So again, I'm not gathering any new evidence and I'm not building an argument. I simply see what its opposite is, and I'm able to know something about the truth value of what that opposing proposition will be. Conversion and obversion help us uncover the full meaning of a proposition by seeing its implications, seeing other propositions that are consistent with the original one and other propositions that are inconsistent with the original one. So this is a Sherlock Holmes move, right? He knows one thing and he's able to see, well, that implies this and that implies this, and he's able deductively to reach a conclusion in a particular case. The goal we have on the slide here is to be able to change propositions from one form into another, or to add new propositions that a premise in an argument logically implies. So the example we have on the slide here, all cars are red, fine. This implies that at least some cars are red. That might seem like a truly trivial example, but more advanced examples become useful, right? So it's not so obvious as saying, well, if every car is red, then at least some cars are red. We find more surprising conclusions as we go, or inferences, I should say, not conclusions. Moving on here. So, logical inference. Let's say a little bit about this word inference. This is a movement of the mind, as Hauser nicely puts it, in drawing a conclusion based on evidence. So this is from the Latin word inferre, comparing with it the word ferry, so to ferry from one shore to another shore. What you're doing in your argument here, or in our case, in our immediate inference, is going from one piece of knowledge to a new piece by a certain operation. This bears the meaning of carrying or bringing something to or into or against something else. So you might bring a flag into enemy territory, right? So there's some martial imagery for us here. Inferences, which is what we're going to be talking about here, first with immediate inferences. Inferences can be valid or invalid. And we'll say a bit about this. So a valid inference is one in which the conclusion does follow logically from the premises. An invalid inference is one in which the conclusion does not follow logically from the premises. So validity and invalidity is what is at issue when we're talking about inferences, not truth and falsity. And a little bit more on that. So inferences can be valid or invalid. You can't have a false inference. You can have an invalid inference. Propositions are not valid or invalid. Propositions are true or false. So when we say all men are mortal, Socrates is a man, right? It may be true or false that all men are mortal. I don't know. I mean, I'm assuming that, I'm accepting the truth of that. But if counter evidence emerges that undermines the soundness or the truth of that proposition, then the whole argument would go. Right? Same thing with Socrates as a man. Maybe Socrates is a god. I don't know. Right? But I'm holding it to be true for the sake of argument. And then the claim is that if all men are mortal and if Socrates is mortal, therefore it follows validly, right, that Socrates is that. I have on the slide here, I can say that's a valid argument, right? So I might acknowledge that a person is making a valid argument. They're following the rules of logic. They're reaching a valid conclusion. But that doesn't mean that I accept that the conclusion is true, right? I'm just accepting that the argument makes logical sense. It could be the case, as in the case of Socrates and all people being mortal, that one of the premises is untrue. I mean, I would be inclined to say that those two premises are true, but if you do have a premise that is untrue and you don't know that and you build your argument on its basis, well, it's like building a bridge with one of the supports not being stable enough to hold the weight. The bridge is not going to hold up, and neither will your argument. So I've already referred here to immediate inference, and I say on the slide, this is what we're going to start with opposition, conversion, and obversion. So take an example of what we're going to be seeing in this mini series. If all cars are red, and that's going to be my annoyingly repeated example throughout these lectures, if all cars are red is true, then no cars are red is false, right? I don't need to build an argument. The term we'll be introducing soon is middle term, right? I don't need that. The conclusion follows directly from the structure of the first proposition. If I say all cars are red is true, then I can know that no cars are red is a false statement. And that doesn't make me a bad person. It just means that logically speaking, it cannot be true. Mediate inference is different from this, and that's what we're going to get into after Lecture 14, when we start talking about the logic of arguments. There, we're going to be building arguments like all men is mortal, all men are mortal, Socrates is a man, therefore Socrates is mortal. That's an argument, a syllogism, as we'll learn. And in that case, there is a middle term that is somehow connecting the subject of the conclusion with the predicate of the conclusion. That's not what we're doing here, but that's where we're headed, right? So really, the rest of the class is going to be about inferences in one way or another. I say the class, the series, either way. Okay, let's talk about opposition. That's our task in these remarks, focusing on the proposition, all cars are red. Okay, so I want to know, what is the opposite of the statement, all cars are red? Statement, I should say, the proposition. We'll focus on the structure of the proposition. So this should say, all cars are red is an A proposition. Question then, is the opposite of this proposition, all cars are red, no cars are red, which seems to oppose it, right? Or some cars are, in fact, red, right? Which also seems to oppose it. The answer is that both of those are opposites of the initial proposition. All cars are red. They're just different kinds of opposites. And that's the interesting thing that we're going to look at in this lecture. It's an opposite is not only one kind of thing, it's at least, well, 5 kinds of things, actually, as we will see. Or I should say, there are 5 kinds of operations that you can perform on any proposition to determine what its opposite will be. There are just 4 kinds of categorical propositions. So let's review that briefly. Right? We went over this in an earlier lecture. You have A propositions. All cars are red. That's universal affirmative. You have E propositions. No cars are red. That's universal negative. And then you have your particular propositions. Some cars are red, affirmative, and some cars are not red, affirmative. So in each case, then, an A proposition can be opposed by an E, an I, or an O. An E proposition can be opposed by an A, an I, or an O, and so forth. So each proposition can have, logically, 3 kinds of opposites determined by means of 5 kinds of operations. And the 5 operations are here on our beautiful chart. And I'm so happy we have this chart. I don't know what we would do without this chart. The square of opposition from Aristotle. So let's just do a little initial introduction to the square, and then we're going to look at each of these things in more detail. Contradictions, we have the word contradictory down the middle. That pertains to the diagonal, and it can go in either direction. So let's start with the upper left. All humans are rational, right? What is the contradictory proposition to that? The contradiction of that, it is the lower right. Some humans are not rational. And it goes in both directions. What is the contradiction of some humans are not rational? Well, it is A. All humans are rational, right? Contradiction is the strongest kind of opposition, and we'll start off by talking about that one. You also have the next 2 operations, which are contraries, and that runs along the dotted line on the top of the square, and what are called subcontraries. That runs along the dotted line on the bottom of the square. So contraries are about universal propositions between A and E or E and A. In that case, you have a universal affirmative and a universal negative, right? We'll talk about that. And at the bottom, you have particular propositions. Some humans are rational, some humans are not rational. And subcontraries are describing the opposition between those. Finally, we have our remaining 2 operations, and those are indicated on the sides of the squares, subimplication and subalternation. Subalternation goes from top to bottom, and subimplication goes from bottom to top. Right? You can follow the arrows on the table there to see where, see what opposition is implied by that operation. 5 kinds of opposition then. 5 things you can do to determine what are the opposite of a given statement. So you have contradictories, contraries, subcontraries, and then subalternates and subimplicants. And I indicate there where on the square they appear, and I indicate which propositions, what kind of propositions are involved in each. So you can pause and take a look, but we'll come back to this at the end. What I want to do now is just walk quickly through each of these 5 and show you, using the square of opposition, how they work. Now, before that, one slide, and this is a table presented in Hauser's book, Logic as a Liberal Art. This table very helpfully, to my mind, presents the truth values pertaining to these different kinds of oppositions, right? So, in the case of a contradiction, for example, we'll just look at that one briefly and return to this as we go through. If the first proposition is true, then you can know with certainty that the second proposition is going to be false because it is a contradiction. It always holds that a true first proposition leads to a false second proposition, and vice versa. In the case of a false first proposition, you can know that the second proposition is going to be true. Now, that's a little different, just briefly we'll see, with the contraries, right? If you start with a proposition that is true and you go to the contrary of that, you can know that the second proposition will be false. Fine, right? But here we introduce a different element. If you start with a proposition that you know to be false, right? You've looked at the world, you've determined that this proposition is false, then when you perform this opposition, this what do we call it? This operation, right? And you determine the contrary of that false proposition. You can't know whether that contrary is true or false. So U here means undetermined, as indicated in the key on the bottom, and T and F, of course, mean true and false. So this table is going to be very useful, and we'll be reproducing this on later slides as well as we talk about each of these 5 operations. Okay, let's start with contradiction. Right? So I want to determine what is the contradictory proposition to any given proposition. Well, in the case of an A proposition, as we saw in the square, you go down diagonally, and the contradictory proposition is an O. So you go from all cars are red to some cars are not red. Now, this might all seem, of course, very abstract, but think about this. If I make a claim that, I don't know, everyone there was on the soccer team, and you're like, no, but Susie was there and Susie's not on the soccer team, some cars are not red, some people are not on the soccer team, then you have contradicted my statement, right? So you have shown that my statement can't be true. That's why the truth value of contradictions are always opposed. Well, the true first proposition always leads to a false second one, and a false first proposition always leads to a true second one. These are, as Hauser puts it, opposites of each other to the maximum degree possible. If one is true, the other must be false. And then I'll end each of our little discussions of these operations with in sum, right? Contradictory propositions are imposed in both quantity and in quality. So we go from all cars to some cars, and we go from red to not red, right? For this reason, they are incompatible in truth. They cannot both be true, and they're also incompatible in falsity. They cannot both be false. So this is the strongest kind of opposition you can come up with. This is basically presenting a counterexample. If someone makes a universal claim, and you're able to present an example of something that is not in line with that claim, then you have potentially disproven their claim, right? You've come close to refuting that claim, at least. So we can see here on the chart, so I'm going to keep reproducing both of our charts here, from A to O and from E to I, and that goes in both directions. You have across the diagonals contradictions, and you're able in the truth table to see the values of those things. But we've talked about this a bit already. Let's look at contraries. I think of this as like the neener version of opposition. It's not quite as strong as a contradiction, right? So if I say all cars are red and you say no cars are red, it's not you're not really refuting me. You're just saying like no, right? I say yes it is, and you say no it isn't. I say yes it is, and you say no it isn't. It doesn't really get us anywhere. It's not quite as strong as a contradiction. Like you can't refute somebody by just blanketly denying what they say. These are found, if we want to talk about our square, along the top of the square. They do strongly oppose each other, as Hauser reminds us, but not to the maximum degree. A couple options here. So if all cars are red is true, then it's impossible that no cars are red, okay? Because I'm acknowledging it's true that all cars are red. So we can know that the contrary of a true proposition is going to be false. But remember what we saw about proposition's truth value being undetermined. What if all cars are red is false, right? In that case, is the contrary proposition, no cars are red, is that true? Is that false? Or is that undetermined? Well, the answer is undetermined. And think about this. If I know it is false that all cars are red, fine. Well, it could be the case that not a single car is red. It could be the case that 2 out of 5 cars are red or 4 out of 5. I really don't know. I can't determine anything with certainty based on a false proposition by using the operation of contrariety, of determining the contrary. Therefore, in sum, contrary propositions are opposed in quality, all and none, none and all, but they're not opposed in quantity, right? So that's why they're incompatible in truth. They cannot both be true, but they are compatible in falsity. They can both be false, or one false, one true. If you start with a false proposition, you can't validly determine whether its contrary is true or false. So going back to our table here, we can see that along the top here, we have all humans are rational, no humans are rational. These are contrary propositions, and we're reminded again of the truth table here on the right, that a true proposition can yield a definitely false contrary, but a false proposition cannot yield a contrary that you know to be true or can't really tell you anything. All right, so we're on to our third operation here, subcontraries. So before we were along the top of the square, and now we're going to be along, where's my finger here, along the bottom of the square. Right? So here you're dealing with particular propositions, I and O propositions. So you have some cars are red, some cars are not red. On the slide, ask yourself the same 2 questions. If one of these propositions is true, what about the other? If one of them is false, what about the other? The question here is a little more tricky because it's not what the truth of the other proposition might be, but what it must be. And actually, that's been the case throughout. In these inferences, we're not determining something that is probably true or likely true. We're determining something that if our assumption is correct, and that's where the if enters here, right? If our determination of the truth or falsity of the first proposition is correct, then necessarily the second proposition is going to have the truth or falsity indicated on the truth table. So we're dealing here in necessary knowledge, not only in opinion or probable knowledge. So looking at these options here, if the I proposition, in our case, some cars are red, is true, then is the O proposition, some cars are not red, also true? Well, we can't be sure. Because if you have some cars and you say some of those cars are red, unless you have further information, you can't determine. Maybe it's the case that all the cars are red, right? And I can't know that logically without more information. Let's look at if it is false. If the I proposition, some cars are red, is false, then is the O proposition, some cars are not red, also false. And we have here, if it is false that some cars are red, then it must be true that some cars are not red. Why? Because if I know that not a single car is red, then it must be the case, if I have cars, that some of those cars are not red, because none of them are red, right? So in this case, going back to our truth table, we'll do this in a moment, in some, subcontraries are opposed in quality, but not in quantity. So quality is affirmative negative, and quantity is universal particular. So these are both particular, right? But one is affirmative and one is negative. And this is why Hauser gives us they are compatible in truth. They can both be true, but they are incompatible in falsity. They cannot both be false. And we're reminded of this on our table for subcontraries, right? So if the first proposition is true, then I cannot determine whether the second one is true. But if the first proposition is false, then it follows that the second one is true. So, good. Okay. We're actually gathering our last two. So we've done 1, 2, 3. We've done opposition, contraries, and subcontraries. And now we're wrapping up with what are called subalternates and subimplicates. These are the last two of the 5 operations that you can perform on a proposition to determine what its opposite will be. So for these two, subalternates and subimplicants, the direction we're going in the square actually does matter, right? For contradiction, you could go down or up the diagonal. For subcontrary, you could go to the left or to the right, and for contrary, you could go from the left to the right, either way. Here, not the case. Subalternate always goes down in direction, and subimplicate always goes up in direction on the square, as we'll see in just a moment. So to consider, if you're going from, now you're starting in the upper left of the square, an A, and you're going down to an I. So all cars are red. You're going for the affirmative particular proposition that some cars are red, right? And in the case on the other side, you're going from the E, no cars are red, down to the particular negative, some cars are not red, right? So for subalternates, when you're doing that, you're moving down the square in that direction. If the universal proposition is true, so it's true that all cars are red, then the particular proposition under it must also be true. So if all cars are red, then it necessarily follows that some cars are red. Easy. That's the example that we started with. But if the universal is false, then the particular, it should say, is undetermined, right? Because if it is false that all cars are red, then I can't determine with certainty whether it's true that some cars are red or whether it's false that some cars are red. I just don't have enough information. So we've already talked about the first sum here, and let's talk about the second one. I'll have to update these slides. For subalternates, we just talked about it, from going universal to particular. But now for subimplicates, if we're going from the particular to the universal, here's how it plays out. If the particular proposition is true, let's say some cars are red, that's true. The universal proposition is undetermined, right? Because just if I say I have 5 cars and let's say at least 2 of them are red, I don't know just on the basis of those claims what color the other cars are, right? I just don't have enough information. But if the particular proposition is false, then the universal must also be false. take our car example again. If I know it is false that some cars are red, then certainly it is not true that all cars are red, right? Because if I'm basically saying no cars are red, right? So we see this on the chart. So if all humans are rational, if I'm performing subalternation, I'm going from universal down to particular. If I'm performing subimplication, I'm going from particular up to universal. And the truth tables indicate here the truth values that we've outlined in these remarks. So here we have, again, friends, our 5 kinds of opposition. So opposites is not just one thing, it's 5 things, right? There are 5 different operations you can perform, and every categorical proposition will have at least, well, will have precisely, in fact, 3 opposites. And that's the 3 directions you can go on the square from each type of proposition. And that wraps up our first discussion of immediate inferences, learning things just based on what we already know without having to build an argument or perform any other observations. So we'll continue with this next time, looking at conversion.